Hello and welcome to another workshop, CSC379. My name is Anthony Hill, and this is our workshop 2. Go through and talk about the brute force algorithm given to find a value m in an m times n matrices. So go through the algorithm, and I'm going to go through the space time complexity. We'll talk about each loop invariant, and maybe give you guys some examples. So today I'm going to be talking about the code given, and we have to, given the matrix of m integers, m by n matrix, find the value v, and is there a square submatrix within the matrix that will add up to v. So the algorithm is check matrix, and each of these for loops will go by step for what it does. And I made some changes to this code in the actual code here. In the beginning, I got rid of the pushbacks and put them in the first for loop, just so that for each iteration of this one, it makes its own for loop, so we could create whatever size we wanted. This is just the test. This is the one that the picture in the slideshow, and this is the meat and potatoes of the algorithm. So we start with n by m matrix. In this one, we're just gonna do a 3x4 for testing purposes, and that gives us 12 squares of 1 by 1, which each loop, the loop will check the first element, and then it will go through each row of m. It'll check each n element, and then it will go through the next row of m and check each n element until all 12 squares are checked. And then it's going to check for the value of v. So in this case, whatever we set our v to it's going to search for it. And after it does the 1 by 1 squares, it'll increase to a 2 by 2 checksum, and then 3 by 3, and it looks kind of like this. So yeah, total of 20 squares in a 4 by 3 or 3 by 4. And each orange square is the 1 by 1s that they're checking. And then each green is the 2 by 2 that it will check and see if we find our value v. And then here's another 2 by 2. So 2 by 2, 2 by 2, 2 by 2. That's 1, 2, 3, 4, 5, 6, 6 2 by 2s. And then for the 3 by 3 squares, there's only 2, 1 and 2. All 3 by 3 and 3 by 3. And for the time complexity, it's the first iteration of 1 by 1. It's only checking 1 by 1 elements, and then for each time that we use our check my matrix, it's gonna every time the I increases, we're gonna be doing more and more elements. So the 1x1s, and then checking 2x2s, 3x3s, and yeah. So eventually we're gonna get to big O of n to the fifth, and well, n to the fourth times our m or our k, which is roughly k to the fifth, or n big O of n to the fifth. And the space complexity, it's constant since our variables don't change. The number of our variables based on the input is unchanged. And go do a couple before I do the loop invariance. We'll do a couple tests. So we'll test for this one, we'll test 50, which it probably won't find, and then we'll test a 2. So a 3 by 4. So a 3x4 matrix we'll check here. And yeah, so let's see what happens. We've got an error for some reason. I don't know why it does this. Okay. Just close and reopen, I suppose. Okay, 3x4. Let's try this again. Maybe it works this time. Okay, for some reason it's not working. Well, it doesn't show the whole matrix, but it does show. It's not showing. It shows the current check size, and it's checking for 100, which it's never going to find. I'm not sure why it's not working right now. Code blocks is messing up. But the current check size, after we try to find that, it says nope, we can't find the 100. And then we do the check for 2, and it checks. So our m and n are 0. The our m row and n elements are 0, and then it moves over 1, moves over again, and moves over to the third, which is how many elements we've got for our n. Then M increases, we check again, checking the sum is 1. And then eventually we get to the row with 2, and it checks the first element, and it's equals 2. So V equals 2 when we find our sum. And I have not run into this problem where it just cuts off half of the code. I don't know why it's doing that. But anyways, back to the slideshow. Apologize. So yeah, space complexity, it's constant. Like I said, loop invariance. So for the first one, we add up the sums of m times n. So this is our very inner loop. Every element in the submatrix to the left of the index will be added, and there are no elements in our current submatrix to the left of J for initialization. Then maintenance. Each iteration of the loop, we add the element as an index to n, at index n to the sum. Therefore, the loop invariant is maintained. And termination, when n gets to the last element, all of them are added up. Therefore, our invariant is maintained. And for the next for loop is the one right above it. We have everything above row M has been added when we start off, because we don't have any rows above M. And with for maintenance, for each iteration of the loop, we add the elements of row M to the sum. Therefore, the loop invariant is maintained. And when M is on its last element, every element above the row M has been added. So our loop invariant is maintained. For the next for loop, every submatrix of our current size to the left of J in row I has been checked to have the sum equal to V. And this is true because it starts at 0. So hasn't checked yet. And then maintenance, with each iteration of the loop, we check the submatrix row I, column J. Since the submatrix has been checked, the loop invariant is maintained. Termination, we'll have checked each submatrix in row I. And for the next for loop, every submatrix with its top left corner has been checked for the sum V. And what this is saying is the top left corner for these loops, it's for the starting point. So it creates a square that says we can start in this element or this element only. And this is as this square decreases, or as this square decreases, the size of our checking submatrix or checksum is going to increase. So as it gets smaller, we have less starting points to start from. Our top left corner will be our starting point. So as it decreases, the checksum gets bigger, go 2 by 2 and then to 3 by 3. And also I forgot to mention in the time complexity that the math.min used to find K as constant time. Also, the square brackets operator used to find the elements is also a constant time. And then current size, termination. Eventually, I will have reached the last row in the my matrix. Therefore, we'll have checked each of the submatrix in the current size of my matrix. And the very last one, pretty much we're done. This is their every submatrix of the size less than the current size has been checked. to see if it equals a V. And it's true because current size starts at 1 and there are no matrices smaller than 1 by 1s. Maintenance. With each iteration of the loop, we run the next loop that will check each submatrix less than the current size. And then termination, we'll have checked every possible square matrix for our value of V. And this is the references. But I want to try this one more time. Yeah, still cuts it off. Okay, well, this time it didn't. So it printed the matrix out and see it. I don't know. It's really weird. This is what it has done every single time. But anyways, this is our matrix. What it was supposed to show. And we've got zeros. This is our n elements in our each of our m rows. And so we test current check size is 1 by 1. And we go by and check each 1 by 1 matrix. And it'll show when we go to the 2 by 2. And when we go to the 3 by 3 to check. And it's never going to find, the first check I put in was 100, so it's never going to find the 100. But anyways, that was my presentation. Thank you for watching, and I hope you learned something.